Hello everyone, welcome back to the Biochem YouTube channel. Today we're going to be discussing glycolysis and gluconeogenesis regulation. We're going to start talking about pyruvate kinase, which is regulating glycolysis. Pyruvate kinase has a type of regulation in the liver and a different type in all other glycolytic tissues. So in the liver, when your blood sugar is low, glucagon is going to be released. Then glucagon is going to activate pKa, that is going to use ATP and is going to phosphorylate pyruvate kinase. And thus pyruvate kinase is going to be in the inactive form. However, if your sugar levels are high, your liver is going to release insulin, and insulin is going to activate protein phosphatase or PP that through a hydrolysis reaction is going to dephosphorylate pyruvate kinase and is going to convert it to pyruvate kinase M, which is the active form, thus activating glycolysis. On another hand, in all other glycolytic tissues, F16BP is going to be one allosteric activator for pyruvate kinase, whereas ATP, acetyl-CoA, and long chain of fatty acids are going to inhibit this enzyme. Alanine, which is a product of the transamination reaction of pyruvate, is also going to inhibit pyruvate kinase. Alright, now we're going to talk about the regulation of glycolysis and gluconeogenesis by PFK1 and FBPase1 in the liver cells, and we have to note that these two enzymes have a reciprocal coordination of these two processes. So PFK1 is going to be activated by ADP and AMP. So when you have energy deficit, you're going to activate this enzyme. So you're going to convert fructose bisphosphate to fructose 1,6-bisphosphate, and thus you're going to activate glycolysis. However, these two substrates, ADP and AMP, are going to inactivate FBPase1. At the same time, if you have a high energy supply, which means that you have a lot of ATP and citrate, you're going to inactivate PFK1. Also, when you have high levels of AMP, you're going to slow down gluconeogenesis, and high levels of ATPs are going to slow glycolysis and accelerate gluconeogenesis. Lastly, we're gonna talk about the regulation of glycolysis and gluconeogenesis by fructose 2,6-biphosphate, and this molecule is regulated by a dysfunctional enzyme which has PFK2 and FBPase2. So when you have a lot of fructose 6-phosphate, PFK2 is going to convert this molecule into fructose 2,6-bisphosphate, and in high quantities, fructose 2,6-bisphosphate is going to activate PFK1. However, when it's in low quantities, FBPase1 is going to be activated. So let's see this other side of the chart, and you can see that when you have a high glucose concentration, you release insulin, and as we said before, insulin is going to go ahead and activate PP enzyme. This enzyme is going to notice how this enzyme is dephosphorylating the bifunctional enzyme. So you go ahead and you leave that serine residue with a hydroxyl group, making PFK2 active. And once you have PFK2 active, you produce the fructose 2,6-bisphosphate, which stimulates glycolysis and inhibits gluconeogenesis. However, when you have low glucose concentration, you release glucagon, and CAMP also increases. And what you do is that you activate the CAMP dependent protein kinase, which phosphorylates the dysfunctional enzyme. So you place that phosphoryl group activating FBPase2. And what this does is it decreases the concentration of F2BP, inhibiting glycolysis and stimulating gluconeogenesis. And these are the main enzymes for glycolysis and gluconeogenesis. Thank you so much for listening. If you have any questions, go ahead and you can text it in campus wires or go to office hours with Dr. Asman. Have a good day. Thank you so much.